Commonly, nuclear reactions are occurring in this and their chemistry is not fully studied. The elements after uranium are called transuranium elements after uranium. Okay. Now finally, problem number 3. Here the two elements are given, Z equal to 117 and Z equal to 120. The question is, they have not been placed or discovered. In which group you are going to place after discovery of them in the periodic table with the electronic configuration in case. So we see from 3.2 that element with Z equal to 117 would belong to halogen. Up to 116 we have seen so far. After 116, starting with 117 it will be, or up to 116 it is halogen family. Okay, with Z equal to 117. Now group 17, I can place these element in group 17. Okay, and the electronic configuration would be Rn. Okay, and 5f. In f orbital 5 electrons are present. Okay, now 146, f5f 146. Okay, 5f 146 and D 107 electrons, S 27 electrons, P 5 electrons. Elements with Z equal to 120 will be placed in group 2, which are alkaline earth metals and will be having electronic configuration and 8s2. Now let us see the next coming one, metals and non-metals and metalloids. In relation to displaying the classification of elements, S, P, D, F block elements shows another broad classification of elements and their properties. The elements can be divided into metals and non-metal. Metals comprises more than 78% of the all known elements appear on the left side of the periodic table. Metals are usually solids. Metals, let us take out them. They are solid at room temperature. And mercury, let us take it. If we take the mercury, it is an exception. And whereas gallium, let us take, and cesium, let us take, they also have very low melting points. The melting point of these two elements will be 303 Kelvin to 302 Kelvin. Metals usually have a high melting boiling points. They are good conductors of heat and electricity. They are malleable, which means can be flattened into thin sheets by the hammer. Let us take the hammer, make them into sheets. That is called malleability. After that, metals are very ductile in nature, which means can be drawn into wires. In contrast, non-metals are located at the top of right hand side of the periodic table. In fact, in horizontal row, properties of the elements generally changes from metallic to on the left side to non-metallic on the right side. Finally, what I am saying, non-metals are usually solid gases at room temperature with a low melting point and a boiling point. Now, in case of boron and carbons are exceptions. They are poor conductors of electricity. Most non-metallic solids are generally brittle and are neither malleable or nor ductile, which means elements become more metallic as we go down to group. Non-metallic characters increases as one goes from left to right across the periodic table. The change from metallic to non-metallic character is not abrupt. I will show you in the zigzag manner in periodic table. Elements with silicon, let us take them silicon and germanium, arsenic, antimony, beryllium. Bordering this line and running diagonally across the periodic table shows that properties or characters of both metals and non-metals. Now, these elements are called semi-metals or metalloids. Finally, I have a problem here. Considering atomic number, let us take it and position in the periodic table. Arrange the following elements in increasing order of metallic character: silicon, beryllium, magnesium, sodium and phosphorus. And let us take the solution for this. We ought to arrange the following elements in increasing order. Metallic character as it increases when you go down to the periodic table and decreases when you move towards left to right. Hence the order of increasing, phosphorus will becomes at first silicon and beryllium and magnesium and sodium. This is the order, increasing order. Finally, property trends in properties of element. There are many observable patterns in the physical, chemical properties of elements in a group or as we move across period in periodic table. For example, within a group or a period, chemical reactivity tends to be high in group 1 and metals, lower in elements towards the middle of the table, and in increasing to a maximum in the group 17th metal. Okay, group 17th metals maximum increase commonly observed. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of non-metals, halogen, reactivity decreases down the group. Now, but do the properties of elements follow these trends, and how can we explain periodicity? The answer is, these questions we must look at the theories of atomic structure, properties of the atom. Now, in this section we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. As you know that trends in physical properties, there are numerous physical properties of elements, such as first one is melting point and second one is boiling point. I will give you the definitions for each of them. And heat, one of the character, and heat of fusion and vaporization, energy atomization, and which shows periodic variations. However, we shall discuss periodic trends with respect to atomic, ionic radii, ionization enthalpy, electron gain, enthalpy, electronegativity. Now, atomic radius. What do you mean by radius? Let us take this as an element. This is called as a radius. Okay. Now, you can well imagine finding that size of an atom, the size of an atom is a lot more complicated than the measuring radius of a bomb. So, first, because the size of an atom is approximately, if you see, 1.2 angstroms to 1.2 into 10 to the power of minus 10 in radius. Okay. So this is very small as we have seen so far. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. Now, in other words, there is no practical way by which the size of an individual atom can be measured. Now, in case of, however, estimate the atomic size can be made knowing the distance between atoms in the combined state. Atoms, when they are combined, the distance is too far and the distance is very small. And if atoms are, okay, if the distance is more in between the two atoms, so there is a combined state. So the combined state or non-combined state depends upon the size of the distance in between the two atoms. One practical approach to estimate the size of an atom or non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule. If there is a single bond, here single bond I have mentioned so far. If there is a single bond in a covalent molecule from this value, the covalent radius here we can see, and the element can be calculated. Finally, for example, the bond distance in the chlorine molecule Cl2 is there. So is 198 pm, and half this distance 99 pm is taken as the atomic radius. Why? Because 198 by 2 equal to 99 pm. Okay, atomic radius of chlorine is 99 pm. For metals, we define the term metallic radius. If you take the metallic radius, which is taken half the internuclear distance, which means distance between one nucleus, one atom nucleus and another atom nucleus. This is the nucleus, imagine that. So what is the distance between two atomic nucleuses? That is called internuclear distance, separating the metal cores in the metallic crystals. For example, the distance between two adjacent copper atoms in solid copper is 256 ppm. Hence, the metallic radius of copper is assigned value of 128 pm. Now, of course, we know very well, for simplicity in this book, we use the term atomic radius to refer both covalent and metallic radius, depending on whether the element is non-metal or a metal. Atomic radii can be measured in a X-ray or other spectroscopic methods. Very important statement that you have to mention. Atomic radii of a few elements are listed in table number 3, and I will show you that table. Two trends are obvious. Okay, nuclear charge and energy level. Atomic size generally decreases across the periods. Okay, for the elements of second period. Now, it is because within the period outer electrons are in the same valency shell and effective nuclear charge, you can see here, and increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Now, within a family or vertical column of the periodic table, atomic radius increases regularly with atomic number as illustrated. Now finally, what I am telling you, for alkali metals, halogens, as we have discussed the groups, the principal quantum number n increases and the valence electrons are farther from the nucleus. Okay, here increases the valence electrons are farther from the nucleus. This happens because the energy levels are filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Now what I am telling you, consequently size of the atom increases as reflected in the atomic radii. Note that atomic radii of the noble gases are not considerable here. Being monoatomic, mono means single atom, and their non-bonded radii values are very large. In fact, radii of noble gases should be compared not with the covalent radii but within the van der Waals radii of other elements, as we can compare. Right, here atomic radius pm across periodic table. Atomic period, let us take period number 2, the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Atomic radius is given here. Atomic period 3 and the elements I mentioned and atomic radius. Atomic radii pm down f, and these are units. Group 1, here it is mentioned, atomic radius I have mentioned here. For group 17, atomic radius mentioned here. Now finally, you can see classification of the elements and periodicity in progress. Atomic number on one axis, okay, atomic radius in pm and another axis. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, lithium having highest value, right, and atomic radius is highest in lithium as it decreases to towards fluorine. Okay, in case of atomic radius, atomic number, fluorine to and here lithium to cesium, as you can see it is increasing. So variation of atomic radius with atomic number of alkali metals and halogens. In this graph we can see variation of atomic radius with atomic number across second period. Finally, what I am telling you, you can see ionic radius. Let us take ions and their radius. Removal of an electron from an atom result in the formation of cation. So how it is cation going to be formed? Whereas gain of an electron leads to anion. Ionic radii can be estimated measuring the distance between cation and anions. Okay. In general, ionic radii of the element exhibit same trend of atomic radii. A cation is smaller than its parent atom because it has fewer electrons, while its nuclear charge remains the same. Nuclear charge never going to be changed. Size of an anion will be larger than that of the parent atom. Why? Because the addition of one more electron or addition of one more electron would result in increased repulsion. This repulsion among the electrons and a decrease in the effective nuclear charge. So, whenever the electrons are going to be added, effective nuclear charge going to be decreases. For example, the ionic radius of fluorine or fluoride ion is 136 pm, whereas the atomic radius of fluorine is only 64 pm. On the other hand, the atomic radius of sodium is 186 pm compared to the ionic radius of 95 pm for sodium. There is a great change. So we find some atoms and some ions which contain the same nuclear number, same number of electrons, as we call the isoelectronic species. For example, O2, fluorine, sodium and magnesium have the same number of electrons, 10. Their radii would be different because of their different nuclear charges. Now finally what I am telling you, cation with greater positive charge will have smaller radius because of the greater attraction of the electrons to the nucleus. Anion with greater negative charge will have the large radius. In this case, net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. Problem, it is given here. Let us see the problem and take the solution. Which of the following species will have the largest and smallest size? Magnesium, magnesium ion, aluminum, aluminum ion. Solution, atomic radii decreases across a period. Cations are smaller, as you know that, than the parent atoms. Among the isoelectronic species, the one with larger positive nuclear charge will have the smaller radii. Hence the largest species magnesium, smallest one is aluminum. Finally, this is